Thank you, Chris, for that introduction. My name is Armen Amirkhanian. I'm an assistant professor here at UA. And what we're going to talk about today is going through non-destructive testing and kind of, ensuring that the students actually get something out of it. And my co-authors on this were Eleanor Skelton, who's my PhD student right now. She's a little unique as she already has a PE and worked in the industry for almost 10 years. And then Norb Delat. All right, there we go. Just a short disclaimer. There's commercial equipment shown here. It's not an endorsement or anything. You can read the disclaimer. I would also like to acknowledge John Popovich and Carrie Hall. They're who I learned, for me personally, my NDT knowledge from. And a lot of the exercises here are kind of based on what they've done in their courses. So they've been, instrumental in how I've been able to implement this. And then also Karen Cruz, who volunteered to help me take all the pictures. All right, so we're going to cover first kind of the experiential learning theory that is kind of guiding how we're doing 3 NDT exercises. This is not the only experiential learning theory. It may not even be the best. It's just, it works nicely for these activities because it provides a good framework to put all the different pieces into. And then at the end, we'll go through some lessons learned. All right. So we got, one of these fancy charts. And if you do any educational research, you got charts and charts on top of charts and flow and whatever. Let's just kind of break this down just a little bit in a very general sense. And some of it may not be, explicitly following Kolb or anyone else, but Kolb said, all right, we kind of have 2 aspects to this. We have the prehensive axis, which with apprehension, not apprehension like, I'm arresting you or something, but more knowledge, and then comprehension. And so with comprehension, that's relying on this abstract conceptualization, more like from the classroom, from a lecture, from someone just describing it to you with no props or anything like that, just trying to, describe something. And then on the other end of the spectrum, you have this concrete experience where you are doing something or you are performing something and actually have an experience. In the other direction on this, flow chart, you have a transformation. So you have reflection observation, which is more about how are you internally processing this and going to produce kind of your observation of it. And an example of this is an exam or a lab report or a homework. And on the other end, and this is what we're going to focus on for these NDT exercises, active experimentation. And that's extension, meaning it's going outside of you. And so how are you, the learner, going to take all of the other stuff and actually go beyond just what was covered in class? And so that's what these NDT exercises are kind of set up for. And the reason this active experimentation is so important is when we think about experiential learning, a lot of people, including myself, before I went through the fellowship program, I thought, I teach labs, their experiences, it's experiential learning, haha, free thing on my resume, good to go. But it's not quite that, because we often do lab exercises following steps, like we're baking a cake. We're not actually learning, we're just learning how to read and follow the instructions. And engineers need to know more than just following instructions. So instead of doing, follow steps, analyze data, write a report, and making that an algorithmic just process, we need to do something more. We need to allow the learner to actually implement and think about what they're doing. And so I have 3 little kids. I've watched way too much Frozen than I care to admit, but like she says in the movie, into the unknown. So the key thing here is let them actively experiment. Don't put them in a box. Let them go take the NDT equipment and scan the floor. Let them, scan something that wasn't even meant for. The table. I had one poor student. If any of you know what a Swiss hammer or Schmidt hammer or rebound hammer is, they tried it on their foot to see what the strength of their foot was. It hurt them a little bit, but they discovered the rebound to their foot was 3. I don't know what the PSI correlates to, but you let them experiment. Now, this is not saying you just turn them loose in the lab and say, all right, go do stuff. I'll give you all A's and, we'll all be happy. You'll get amazing teacher evaluation scores, but the students won't learn anything. So we're going to go through how we can kind of structure this, so that there is that unknown aspect. They get that experiential learning, but they also actually learn something. So we're going to cover 3 relatively straightforward NDT techniques: resistivity, ultrasonic pulse velocity, and cover meter. Okay, resistivity. You would teach this in the classroom, say, all right, here's our Wenner probe. We put a known current, we measure voltage, V equals IR, we get resistance, we convert to resistivity through geometry. Okay, so that's kind of the abstract, that's the theory. And then you set aside, all right, for the first part of your lab, you are going to do these prescribed things so that you get that concrete experience, that positive reinforcement in doing the activity properly. You work out any issues using the equipment, you take your measurements, and with resistivity specifically, you get a resistivity. We correlate to chloride penetrability, among other things we could do, and that's half of it. Unfortunately, sometimes we stop at this and we say, all right, look, they measured, this concrete had moderate chloride penetrability. But we need to go beyond that. We need to allow them to see, what does this resistivity, actually do? So one thing that I've done, and, it's interesting, is, all right, let's try to use this device for something it's not meant for. And, that will definitely get you thinking about, what is the device calculating, because you're trying to use it for something it's not meant for. And what I have them do is take a cylinder, and I tell them the water cement ratio of this cylinder is X. And then I give them some other cylinders of same, they were cast the same day, they have the same moisture content, same temperature, because those all affect resistivity readings. And then say, all right, are these cylinders at a higher or lower water cement ratio? Now, that's kind of hard to do because you can't look in the instruction manual and see how to do it. They can easily take the physical reading, but then they have to actually think about, all right, do I need to take this reading first and then calculate, or do I need to look at a trend in the data? What am I trying to do to find out this water cement ratio? So they start thinking about, what is the resistivity value actually measuring? And in the lecture material, you talk about pore space and the pore solution conductivity and so forth, so that they would have that background and would connect it, ideally. Now, that does not always happen. And so it is really important for anything experiential for the instructor to be an active guide in this entire process. You can't just give the students this problem and then walk away and expect them to figure it out. You have to kind of be there and actively guide them. Maybe ask them questions, leading questions. If you're a lawyer, this would be second nature, but you ask them questions to get them to think towards the answer. But you don't want to give them the answer directly. They need to kind of get to it through this experimentation with the knowledge they have and the physical environment they're in. So we've done that, and it kind of works. Students sometimes get really creative with how they think about it. And so, again, it's important that you're actively involved so you don't let them go too far off, in left field. And then, like Lisa mentioned earlier, they actually learn worse because they completely missed the boat. So you have to be there actively engaged with them. Next one, ultrasonic pulse velocity. Again, another simple NDT technique. But when we are going to use it in this learning environment, we can actually do some cool things with it. So the transducer sends, in this case, a 54 kilohertz pulse through the concrete. You pick up how long it takes to go from one transducer to the other. You calculate velocity because you know the distance, and you can estimate modulus and compressive strength from that. The presence of cracks will decrease the time it takes for the signal to get to one transducer to the other, but it depends on what the orientation of those cracks is. And in some case, your concrete could be cracked to pieces and you still get a good reading because they're all parallel to the direction of the propagating signal. So you teach that. Again, you're going to teach them the theory of this. They go into lab, they measure a known cylinder, and they can also practice, and I mentioned this in the document, they can practice the calibration process. This is also sometimes overlooked because, well, laboratory equipment can go out of calibration. You got low batteries or something, you know, so it's important to also teach that. And then we come again to the experiential part. Again, unknown cylinders, but this time, instead of unknown water cement ratios, they have identical mix designs, but they were all loaded to different levels. And you see here, it's 0, 50, 75, 90, 99, 100%. Okay, well, first of all, hold on. How are you loading to 99% peak load and then another cylinder to 100% peak load? Yeah, it's pretty much the same. But that's the nice thing about this is when you get to 100 or even 99%, you likely have visible cracks. And it's awesome when you see the students realize they can actually use their eyeballs in addition to the NDT equipment and say, can I just say it's 100 because I see cracks? I'm like, well, you can. I mean, that's part of non-destructively evaluating something. So they're kind of thinking outside the box a little. But when we look at the 99 and like 90% or even 75%, it gets really interesting because it's actually kind of difficult in a specimen like this to always be able to differentiate those three. And so they have to go and think about, how am I going to test this? Now, I showed in this one here that we're testing the cylinder both transversely and longitudinally. So they are doing that as part of just the normal process of learning ultrasonic pulse velocity. And then when they get to the unknown, it's important for the instructor to kind of guide them and think, all right, if it was loaded, top and bottom, which way would the cracks likely be? Which would be the best way to test this? Because I can get readings from everything. So I have to think, all right, I would most likely see differences in transverse or longitudinal, and then really focus on taking those measurements. And again, as the instructor, you're going to be there actively guiding them, getting them to think about what they are trying to do. And when they come up with essentially the ranking of which specimen was 0, 50, and so forth, you will kind of work with them and say, all right, you took all these readings in these directions. How are you going to use that to help you evaluate this order? And oftentimes what you'll see is that the longitudinal readings are usually pretty consistent. You will likely get almost all the readings within the coefficient of variation of the measurement, especially with students, because they don't do a good job of lining up everything consistently. But the transverse is where you'll see the separation in the data, if, again, they ran it correctly. But that's why you're there helping them kind of think about how they're going to take the classroom and actively do this activity. Now, and I'll mention this in the lessons learned, it's shown, the photo shown here is on 4x8 cylinders. That's a horrible size, as I discovered. If Chris wants to ask a question, what would I not do again? I would never use a 4x8 cylinder. It was awful that you could barely distinguish anything. 6 by 12 is the way to go. But we'll get to that in the lessons learned. All right, and finally, cover meter. This is a very simple device. It's essentially a glorified metal detector, has other features. It can detect bar size and sensitivity, to all this sort of stuff. You teach all that in the classroom. And for the concrete experience, the prescribed experience here, you have them actually measure known bars with known offsets or covers and, start graphing it and looking at the data. Now, we found the best way to do this is to use a non-magnetic material like wood or styrofoam. And if you have pieces that are all the same thickness, you now have nice spacers that the students can very quickly take a series of measurements, and they're not sitting there trying to take a tape measure and measure every little thing and introduce some error into it. So for this part of the activity, it's really nice to have everything kind of set up ahead of time for them so that they can really focus on the actual measurement of the device and not the miscellaneous measurements. You ask them to plot the data in a prescribed manner so that they can kind of reflect on what they've observed, and they see that the performance of this kind of device is not linear with depth. As the bar gets further away from the sensor, it doesn't just the signal doesn't just drop off in a linear fashion. It's nonlinear. And that's important because when they get to the next part here, they should start thinking about, if I get a low signal, that could mean it's 2 inches down or 5 inches. I don't know, because there's a nonlinear effect of depth and the signal strength. And then also looking, at the effect of depth and the bar size that the device is actually thinking is there. And one thing that the students are really surprised to see is that the bigger bar has way more scatter when that bar is really close to the surface, because the impact of such a large presence of a ferromagnetic material causes the reading to be very scattered, depending on precisely where the student placed the sensor. And so they'll have large variation, then it actually gets better with depth, unlike the smaller bars where they see increasing variation as the depth increases. But that's all like very prescribed, guided. And then, and this is one of my favorite activities, we give them a box. We make a mystery box for them. And I like this because it used a bunch of scrap wood from a renovation I was doing at my house. So I didn't even have to pay for it, just threw it all together. That's why the box is that size. It just happened to be the boards left over. But all the students know about this mystery box is that there is rebar inside. That's it. They don't know how much, what bar size, how deep, how shallow, nothing. Now here's what's inside. The goal of this is to tell the students, all right, you now saw how the sensor reacts to known bars and signal strengths and all that. Now here's an unknown box. Let's go scan it, and you tell me what's in the box. Now, this is really nice because there is a single correct answer, unlike the other ones where, depending on how you're good at compressive strength or resistivity stuff, you could get a range. But this has an absolute single correct answer. And you'll note many things. We're going to cover this in lessons learned, why this box looks kind of interesting. But the students scan the box and have to come up with a schematic. Here's an actual student submission for that lab where they measured everything. And this one got pretty much dead on. This happened to be Eleanor's homework submission. She has a PE, so she was a little more detail-oriented than normal student. But the other students did very similar. And actually, and this surprised me the most, they were so dedicated for this one assignment because they would come into the lab. I gave them access to the lab. They can come in whenever they wanted. And they spent, in some cases, hours just ensuring they got everything right. And I think personally, the fact that it was unknown to them, like a complete mystery, they couldn't even see, have a sense for how many bars or anything like that. It really turned it into a game, almost like a treasure hunt for them to kind of find out, all right, what's going on here? And so this actually turned out to be one of the best activities we did in the NDT course so far. And again, you may have to guide them a little bit on this. Some students, I was careful with where I put metal screws and so forth. I'm not a good woodworker, so I couldn't use like nice joinery and dovetail joints and all that. So there were some metal screws. Some of the students picked those up. I said, no, don't go right to the edge, just kind of look in the middle. You guide them a little, but they actually did really well with this. Okay, so lessons learned from these 3 activities. Resistivity. If you're not familiar with resistivity measurements, like you're teaching this course for the first time, oh my goodness, you better make sure all those cylinders are at the same moisture level. It doesn't matter what it is, it just needs to be the same and not air dry. Don't let it get air dry. Ideally, you'd keep it in a line bath. That just ensures everything is consistent. If you have a vacuum saturator, that works too, because then you just toss it in like an hour before lecture and call it good. When you do this enough, you'll notice that the values, and when you're measuring even the same cylinder, like here in the picture, they can drift. As the water evaporates from the surface, you have a disconnection of some of the electrical pathways. You also have a slight cooling effect from the evaporation of the water, and resistivity measurements are extremely sensitive to temperature, and that can actually cause the values in the device to slowly drift over time. So if students are not quick, you'll see that, and they'll start asking questions. I actually had the grad students in that course come up with theories as to why they thought it drifted, and most of them actually got pretty good or had pretty good answers. Finally, batteries. Some resistivity devices are battery operated. Sometimes the batteries will get low enough that it gives you weird answers, but not low enough that it triggers the low battery alarm on the device. So, just make sure that's more of a practical thing. Ultrasonic pulse velocity, as I mentioned, you got to use 6x12 cylinders. Those 4x8s, oh my goodness, it doesn't work that well. You get very little separation in your data. End grinding the cylinders is important. You could technically not need to end grind the cast bottom of the cylinder, but the top, for sure you want to end grind. No amount of Vaseline will be good enough to give you a consistent signal. And absolutely do not use sulfur capping. You'll have a acoustic interface there, and that's going to really influence the reading. So you don't want sulfur capped cylinders for this. It's always a good idea to calibrate these devices. And then loading the cylinders to 99%, that is tricky. And honestly, you probably overshot or undershot because there's huge variation in compressive strength. Just do your best. The way I've done it personally, the 99% load, I watch the load increase. And once it gets near the peak, as soon as I see a drop, I'll stop. And for the 100%, I'll let it go till I audibly hear a crack. And then I'll stop that. That may not be exactly consistent, but it's something, to give us some data. And it's nice for the students to see that, well, 99% and 100% in some cases are the same. So my, NDT technique isn't that precise. With the cover meter, rings, bracelets, piercings. One student had a navel piercing and was holding the device, near their stomach, and our device will not randomly, but occasionally recalibrate itself, and it recalibrated to their navel ring, and then they got all sorts of weird data. So, and that's in the instruction manual. Now, this mystery box, it's funny on purpose, like the bars are really high up in the box on purpose. You're going to put this on some surface, likely a concrete floor, It may have vinyl on it, but there's concrete underneath. You don't want the rebar in the concrete floor to influence your measurements. So the standoffs here are about, I think it's like 9 inches off the ground, just to make sure there's no undue influence from whatever surface you're resting the box on. This was actually the biggest thing. I originally made the box and just had the rebar sitting down on the bottom of the box. And when I put it on the concrete floor, it was picking up rebar from the floor. So you want those high standoffs. On the covered surface of the box, indicate an origin. Because students will start at one corner and just go. And if you don't tell them where 0, 0 is on that square surface, you're going to get all sorts of different answers because everyone's left is different. And then finally, for you as the instructor, don't forget the fact that you do have a lid and it has a thickness, which is a cover depth. And I thought all the students had lost their marbles and had calibrated the device wrong because everyone was half an inch off the correct answer. And then I realized I forgot about that. So don't forget about that. Okay. I quickly went through, I hope, and I'd be happy to answer any questions.
All right. Thank you, Armen. So we got time for 1 or 2 questions here. One in the chat here says, did you try to do the mystery with concrete too?
All right. Hey, Chuck. So I have done cover meter on a reinforced concrete floor with them having no knowledge. I have the advantage that I have a portable GPR unit, so I could confirm the rebar location and size separate from the cover meter. Because what you'll find in especially floors, well, at least our floors, you'll pick up all the not tie bars, the metal ties that connect the bars together. Forgot exactly what those are called. And that will really sometimes throw off that cover meter, especially if it's densely reinforced and they used a lot of tie to get it all there. So I have done it. The students got a little frustrated because they couldn't make sense of the data. But then they confirmed what was there with GPR, and that really helped a lot more. So.
Okay. Armen, one question / comment that popped in my mind. You said that they were, trying to guess, where all the rebar was in that last one you were doing there. The game of Battleship kind of comes to mind. You're doing that. Have you ever thought about having groups of students kind of set up their own boxes and compete against each other to see who can get closer?
That actually sounds like a really good idea. Like a really good idea. Because I could just give them empty boxes and the rebar pieces and ask them to set it up some way. Now, one of the lessons I didn't put in, once you make your box and you put the lid on, you should check that your cover meter that you're using can actually detect all the bars. The big bar you see here was actually lower and my device could not detect it. And I'm glad I checked before giving it to the class because they would have been really frustrated. So yeah, but I like the idea. Give everyone, a chance to kind of challenge each other and, find stuff.
Makes it a little competitive. Can be fun.
Yeah.
Cool deal. Well, Armen, thank you so much. Great presentation.